Hi everyone, my name is Daniel Cohen. I am a current postdoc at Brown University, and today I'll be presenting our work in incorporating efficient uncertainty and calibration modeling into our deep retrieval architectures. And this work was done with my colleagues Bhaskar, Oleg, Navid, and Karsten. And to motivate why we want uncertainty and calibration in our models, I'm going to present an example we all know and love, a ranked ordering of documents. And in this setting, we get some notion of relevance. The first document is clearly more relevant than the remaining documents, and the third document is less relevant than the first and second and more relevant than the fourth. But we don't really know how relevance changes. It could be that none of the documents are relevant, or only the first document is relevant and all of the other ones are extremely non-relevant. To get some more insight into this, we can look at the output of our model. And if we try to tease apart how relevance changes, we get a little bit more understanding. The first three documents have this nice linear decline in relevance, and our last document is extremely non-relevant. But we're making this assumption here that there's this linear relation between our model score and relevance, but we're working with nonlinear architectures, so there's nothing that says that this is the correct view. And to really drive this point home, I want to present a nice thought experiment where we have two models processing the same query with the same documents, and they output the exact same ordering of documents. So by any standard evaluation metric, they are exactly the same performance-wise. But if we take a look at the actual scores these models output, they tell very different stories. Model A suggests that all the documents are extremely relevant, or at least they're very similar with respect to each other relevance-wise. Model B suggests that only the top two documents are relevant and all the other ones are irrelevant, or there's this equal degradation of relevance. It's difficult to tell. And there's another layer of ambiguity. If we just zoom in on Model A, well, the document scores will start appearing farther apart and it'll look like Model B. And so there's really no way to tell which model is correctly portraying relevance with respect to each document. And there's just a lot of confusion. With that in mind, we propose modeling uncertainty directly. So we have the same setting, a model with each line as the score of a document, but rather than relying on this, we propose modeling every possible score of the document. And we get this nice distribution, which reflects the confidence of our model. And instead of this linear interpretation we assumed in our motivating example, we see that the model is only very certain about its first few documents and this rapid decline in confidence. In developing this method, we want our uncertainty to be usable. So we have three core objectives that we had in mind. First, that it should be expressive. So the uncertainties of different documents shouldn't all be identical. So we can make informed downstream decisions and re-rank based off of risk. Second is that we should have improved calibration. That is, the relative relation between scores of each document should tie into their relative relevance with each other and the query. Lastly, it should be inexpensive. It doesn't make sense to only look at a single document. We're interested in how relevance changes and how confident the model is for the query, which requires processing all the documents we planned on re-ranking. Since we're talking about uncertainty, we of course take a Bayesian perspective. And for those of you not familiar, Bayesian inference considers all possible parameterizations of our model. In contrast, the way we normally operate in neural retrieval is you train your model and you get this static set of parameters that you then use forever. Bayesian inference instead considers multiple parameters conditioned on how likely the data supports them. So when we have a lot of data, there's only a few configurations possible, and that's our certain region. And when we don't have any data, well, then the distribution over possible parameters becomes more uniform, and that's our uncertain region. And by sampling different parameters and then passing our input into our model, we can get this distribution over our output score. But this posterior, the probability of theta given our data, is extremely intractable for neural architectures. Fortunately, we are able to perform approximate Bayesian inference, and specifically variational inference, where we learn a simpler distribution Q of theta that tries to approximate the true posterior, which is our theta conditioned on our training data. And there's lots of ways to perform variational inference. We choose concrete Monte Carlo dropout, and we adapt our ranking loss to make sure it meets the criteria for variational inference. And what concrete Monte Carlo dropout does is, rather than trying to readapt how we train our architectures, it's this nice drop-in approach. So you train your model like you would in any standard IR situation, and you get your weights M. At inference time, you sample a Bernoulli distribution that determines which weights you're going to zero out. And then every time you pass your input into your architecture, you get different ones and zeros from your Bernoulli, so you get a different sampled parameter configuration. This seems a little bit complicated, but what you can really take away from this is that we're essentially at inference time performing dropout on our learned weights, and this dropout is configured with a learned parameter P. And if we do this 100 times, if we perform dropout 100 times, well, then we get 100 different configurations for our model, and this induces a Gaussian output. And this is great. We're now able to get, hopefully, an expressive, better calibrated uncertainty for each queried document pair. But this isn't efficient. We're now asking everyone to run BERT 100 times for every single document you want to rank. This isn't feasible. If you had 100 documents you were planning to re-rank with BERT, well, now you can only rank one document, which is a bit trivial. Fortunately, there's been recent work where being just a little bit Bayesian allows us to capture a significant level of uncertainty. To better understand this and visualize it, here's a classifier, a binary classifier, that's completely deterministic, so no Bayesian components. And as expected, the model is completely certain except along the hyperplane. Now, a fully Bayesian classifier has what we want. It's uncertain except where our data supports it. But what's really interesting is if we only make our last layer Bayesian, we get almost the level of fidelity that we get from a Bayesian model for a fraction of the cost. What this means in the case of IR is, rather than running BERT 100 times, well, now we can just take one of the last hidden layers of BERT and pass it into our Bayesian multi-layer perceptron. This is a minimal cost compared to what we were asking before, and we can now re-rank all of our documents with uncertainty. So now that we've established a efficient, hopefully expressive, and well-calibrated uncertainty approach, we need to make sure it's actually useful. And we do this through two tasks, the first of which is risk-aware re-ranking, specifically CVAR. And what CVAR does is it says, let's only look at the tails of our distribution, either the upper or lower tail, and take the mean of that percentile. And this gives us an idea of how risky each document is. And you might think, well, if they're all perfectly normal, this never changes the ranking, and that's correct. But if there's any skew or any difference in the shape of our distributions, well, now certain documents will jump much farther up, and also other documents will drop much further down our rank list, and this is what we're hoping to capture. Our second task is cutoff prediction. In this setting, there's some non-monotonic metric we want to optimize to show our user. So at some point in our rank list, we want to stop showing our user because there's too many non-relevant documents. And we use Choppy, a recent transformer architecture that looks at the output scores for every single document and determines where we want to truncate our rank list. The advantage in case of uncertainty modeling is that we can now not only give the score for each document, but the variance, the skew, and the entropy. And the hope is that this additional information will allow our Choppy architecture to better understand when our model has lost confidence and there are no more relevant documents to show. For our experimental setup, we're essentially asking three core questions. The first is, do empirical results follow theoretical intuition? And the idea is that the mean score for every single document distribution should equal its deterministic version. So by incorporating our Bayesian component, we shouldn't be hurting performance at all. Second is, can we leverage uncertainty information to improve results? And that's done through that risk-aware re-ranking and the cutoff prediction tasks. And lastly, does incorporating uncertainty improve calibration? And this is the relation of document scores. If a document is very similar to another document relevance-wise, well, then the score should reflect that. We ask these questions over three collections: MS Markup Passage, the Trek 2019 Deep Learning Track, and also Robusto 4. And something I want to point out is that we don't train or validate at all on Robusto4. It's used as a way to measure how well our uncertainty method works on a out-of-distribution collection. We look at two architectures, convolutional KNRM and also tiny and mini BERT with 2 and 4 transformer layers respectively. And these architectures represent the two paradigms of current neural retrieval models. We have the neural network with the handcrafted kernel pooling, and then we also have the fully distributed massive transformer. In both cases, we add a 2-layer multi-layer perceptron trained in a Bayesian inference manner. To make sure we actually are doing something useful, we consider both variants, so a deterministic version of our model and also a Bayesian. This is denoted with the subscripts D and B. We also, in the case of cutoff prediction, look at a generative model, and this model tries to directly predict the likelihood of relevance. And so we're no longer dealing with the strange negative infinity to 0 scores. The generative model outputs its score 0 to 1 that's trying to model the probability of relevance. And hopefully this will give some insight to self-reported confidence and the Bayesian reported confidence. With that said, we can now talk about our results. And first is the question, do we achieve the same performance? And there's a lot of numbers here, but the key takeaway is yes. There's some fractions of a percentage where the Bayesian model performs better, other times where it performs worse, but the takeaway is you can incorporate this last layer Bayesian approach without having to deal with your model degrading. And with that in mind, we can now ask the interesting questions, which is, can we actually do something with this uncertainty, specifically this risk-aware re-ranking? And the answer, again, is yes. Based off of NDCG at 200 and NDCG at 20 for Robusto4, we see about a 4% improvement using either the upper or lower tail, which suggests that it's not the skewness that makes the difference. It's the whether a document has a long tail or not that really makes it a risky document. For our second usability task, this cutoff problem, we see again a substantial increase when we incorporate the uncertainty information with about a 3 to 10% improvement. But what's really interesting is that it also works on Robusto4. And with respect to the numbers in the table, it's out of 100%, where 100% represents perfect performance with respect to the Oracle cutoff. Lastly, we were able to ask the question, is calibration error improved? And in this case, lower is better, so 0 is perfect, and 1 is the worst possible calibration you can have. And we see about 30 to 40% improved calibration. But again, what's really interesting is that this this Bayesian perspective of uncertainty is robust enough to handle this out-of-distribution collection. So with these things in mind, we've shown that this uncertainty is expressive, is useful, and improves calibration. But this wasn't a research question, but I want to highlight this, is the efficiency component. So regardless of which architecture you use, BERT, convolutional KNRM, even GPT-3, it'll take about 0.3 to 0.4 microseconds to run 100 samples per document. And this is because it doesn't matter which architecture you use, you're just passing a 2-layer multi-layer perceptron with dropout. So even if we have new architectures in the future, this method is suitable, which is wonderful. So in conclusion, I want to go over our core contributions. The first is we present an efficient Bayesian uncertainty method for deep retrieval architectures, and that this uncertainty is actionable, which we demonstrate with risk-aware re-ranking and downstream tasks. And lastly is that it's able to robustly handle new collections. Thank you so much for watching this presentation, and please feel free to contact me for any questions you might have.